Hello, everyone. Today, we're going to talk about the linear growth model, the Harrod Domar growth model in the textbook. And just note that this is sometimes called the AK growth model, so that if you've seen this in a class in growth, or maybe an intermediate macro class, perhaps, this is similar to what's called the AK growth model, because it simply is a linear relationship between capital as the only input and output y. And we can see that quite simply as being capital as our one input. We could, of course, consider this a composite of different kinds of capital. It could be human capital as well as physical capital, but the one input that we call capital and our output y. For reference, we have the 45-degree line, and an example of what we have in mind is that output y could be equal to 0.5, that is to say, half the value of the capital stock. So that in any given year, whatever the capital stock is, assuming allowance is made for depreciation, that we are able to get 1/2 of that value of capital as an output each and every year, again, assuming that there is some allowance for depreciation. So that is the basic idea. For historical reasons and also for emphasis about the I-core, as I'm going to explain in a moment, in development, this is often called the Harrod Domar growth model. And that's named after Roy Harrod and also F.C. Domar, who were two early economists working in the area of growth, who worked on this problem, and they worked on it in the context of a high unemployment economy, which is how one can think about a developing country in which most workers are in the informal sector. So a key idea then is to formulate the model with what's called the I-core, the incremental capital to output ratio. And it's called C for the symbol. And C, I-core, simply says, okay, for any given amount of increased output that we would like to see, how much increased capital stock does that entail? So, as an example, in the case that we just saw, if we mean for our increase in our output to be 1 unit, correspondingly, how many units of capital will that require? And the answer for the case we just talked about was 2. The I-core then was 2. And it says that if we invest 2 units of capital, as long as we make allowance for depreciation year by year, we will be able to get every year thereafter 1 extra unit of output, or value of output. And so talking about the I-core, we start with the I-core C, the change in capital needed for a given change in the value of output. Having a linear model, it is also the case that the marginal impact is the same as the average. That is to say, the slope relationship is everywhere the same between capital and our output. So that overall, you find the output as being 1/2 the value of the capital stock, and if we want to increase output by 1 unit, we have to increase 2 units, the amount of capital. And so the resulting growth relationship is the change in output will be equal to 1 over C, 1 over the I-core, times the change in the capital. And so let's talk further about the derivation of this model. So start with a last line. This is that y is equal to 1 over the I-core times k. We have a linear relationship, so once again, the change in y is equal to 1 over c also times the change in k. And that's the key point here regarding the linear relationship between capital and output. So looking at this a little further in terms of economic interpretation, then this is telling us, first of all, when we look at the change in the capital stock, I said we've taken care of depreciation. So this must be the same as the net total amount of savings, capital S net. And then we are dividing by C. here. So that the change then in the amount of output is equal to the net savings amount divided by the I-core. Now we want to translate this and begin to think of this in growth terms. So that in order to find growth, we just divide both sides of the equation by y. And the reason for this is that if we start with the change in the value of output and we divide it by the initial value of output, we get the growth rate. For example, if we start with a 1 trillion rupee economy, let us say, and we add to that economy the change of 100 billion rupees, that's 100 billion rupees divided by a trillion rupees, and that is equal to, in this case, 0.1, or the growth rate of 0.1, which is to say a growth rate of 10%. Could be over 1 year, it depends upon what the data actually are. And so that this then tells us that growth here is equal to the net savings rate, which is the total amount of savings divided by national income. That's the rate of savings. And again, divided by C. And so overall, then, the growth can be defined and derived with these assumptions as the net savings rate divided by the I-core. And this is already telling us something that I think is somewhat intuitive, that if we want to increase growth, since growth is driven by investment, then we can see that the net savings rate will, as it increases, increase growth rate, but as the I-core increased in value, that would decrease the growth rate. Why? Because we want to produce with less units of capital if we can, not more. More commonly, when we look at the Harrod Domar growth model, it incorporates capital depreciation. And I'm going to start by showing you the formula that we are going to get to. It is very similar looking to the formula that we had before, but it's important to distinguish the two. On the left-hand side, of course, we have change in y over y, and that once again is the growth rate. On the right-hand side, instead of the net savings rate, we now have the gross savings rate. We divide by I-core as before, and then we have a subtracted depreciation rate. So delta here is the rate of capital depreciation. So we can derive and see where this comes from. Once again, we have our definition of the I-core, and we remember that the change in y is equal to 1 over c times the change in the capital stock. And so, just by the definition, the change in the capital stock, we know, will be equal to the gross investment amount minus the existing capital stock times the rate of depreciation. And that'll give us the change in capital, the net, after we deal with our allowance for depreciation. So then we can just substitute here. What we have just seen is our definition of delta K. We have 1 over C as before, and we just substitute this relation here. And then we multiply through to get that the change in the value of output is 1 over C times the gross investment amount minus 1 over C times the depreciation rate times the amount of capital. Then, again, noting our investment savings relationship that drives what we do here, we see that the growth rate then is, following from before, the amount of gross savings divided by y, as we're dividing on each side of the equation by y, times c, y times c, minus, from this other side, delta y over y. And notice here that the y's are going to cancel. So that this is equal to SG over y divided by c minus delta. as these two y's have canceled. And this gives us our final formula relationship. It says that the growth rate will be equal to the gross savings rate, now rate, divided by the I-core minus the depreciation rate. So we can see the relationships between these things if we look at some made up numbers. So let us just suppose that the rate of gross savings is 1/8. The depreciation rate is 4%, a little bit high by international averages, which is closer to 3%. And we have an I-core of 2.5, which is very common, seen around the world. Just plugging in these numbers to the growth equation we just had, we have 0.125, the savings rate divided by 2.5, the I-core minus depreciation rate. And we find that from these assumptions, we get a growth rate of only 1%. We'll see later that as an approximation, if our population growth rate turns out to be 2%, then this means per capita growth will turn out to be actually minus 1%. We'll come back to that later. Now let's look at some different numbers. Instead, we will let the savings rate be equal to 17.5%. We will put our depreciation rate at 3%, closer to international norms rather. And then finally, we will have our I-core. We'll just keep it the same as 2.5. And this gives us 4% growth. And that's 4 times higher, of course, than we had before. So then let's see how we can do some thought experiments. So in India, they sometimes talk about how they want to raise the target rate of growth above what it is, as many countries in the developing world do. So suppose there's a gross savings rate of 1/5, a depreciation rate of 3%, an I-core of 2.5, a typical number. And so what's the implied rate of growth? Well, we've already seen how to do this. We just plug in the numbers. 0.2, the savings rate divided by 0.25, the I-core minus the depreciation rate. And we find that the answer is 5%, 0.05, or in percentage terms, 5%. So then in India, it's quite often talked about, at least it has been, that we ought to be able to raise our growth rate up to 9%. So in this case, how much would we have to increase the rate of savings? Well, now the savings rate is our unknown. There could be other unknowns. And so we have the unknown savings rate divided by 2.5, the I-core minus the depreciation rate. And we already know now that what we're looking for is a resulting growth rate of 9%. So now S is our unknown. And so then substituting out for S, we find that the savings rate must be 0.3. In other words, if the question is, indeed, how much would it have to increase? We find that it's up by, we can say 10 percentage points, from 20% to 30%. So that is the basic introduction and overview to the Harrod Domar linear growth model. And we'll have a chance to discuss this in class as well.